Hey everybody, it's Dr. D here. Welcome back. If you've been following along with the confidence interval videos, then you know what we did was we talked about the intuition of them, of a confidence interval. What is it? What does it mean? And then we did a numerical example. What I said was kind of the intuitive but the very inefficient way. And I left off saying that the reason is that the z distribution, or the z score formula, is a z producing machine. What we want to do is generate a mu producing machine so that we don't have to do the full setup of the problem and all the algebra. It will get very tedious because it's identical every time. So what we're going to do is we're going to go through an example just like we did with the numerical example, except this time what we're going to do is we're going to take the numbers that we normally have for a problem like this, and we're going to put them in an envelope. And we're going to try to keep that envelope sealed. The longer we can keep it sealed, the better. So what do we want? Let's put, we're going to have alpha. That's our confidence level. We're going to have x bar. That's given. For now, we're still assuming we're going to know sigma x. And we'll get rid of that assumption next time, maybe. Let me put that in here so it fits a little bit better. And then also we'll know our sample size. Now, I don't know what those are yet. They're in there. But I know that at any time, if I panic, I can just open that envelope and all will be revealed. What I don't know is my mu1 and mu2, because that's what the confidence interval spits out, right? What we're trying to do is get to a place where we have mu1, mu2. So there we go. That's our goal. To do this, whenever we would have a problem like this, we would always set it up like so. We've got x bar. It goes in the middle. We have to use our sigma x and our sigma and our n to calculate our sigma x bar. So that would happen. And then what we would do is we would take that alpha and we would try to put x bar at the top end and the bottom end of the middle alpha of the distribution. And if this all sounds like nonsense and you want to understand a little bit more about what these things mean, the previous two videos will walk through what all those concepts are. But the alpha is the confidence level. And so we've got one normal distribution right here where that's a terrible curve, but it'll do just fine for our purposes. Where x bar is at the top alpha, top of the middle alpha, and then we've got one right here where x bar is at the bottom of the middle alpha. And then the center of these is what we actually care about, right? Because that's the center of the distribution. That's mu1, and then this is mu2, and those are our unknowns. I mean, right now we don't know any of them, but x bar is given, alpha is given, n is given, sigma is given. So this is like a template. You can think of this as like a template for how we would work on any of these problems. The further along we get in this process before we open that envelope, the more generalizable this is, right? So far we've already captured the intuition of every confidence interval problem. And if we keep going, we should be able to move things forward. So this is a question, and then this is a question. And now of the 4 steps, step 1 is done. Step 2 is to relate to the standard normal distribution. There's 4 total. And we're going to do the one on the left all the way through, then we'll do the one on the right all the way through, just like we did last time. And I'm out of space, so let's copy this up to the top again. The standard normal distribution, as you will recall, is a normal distribution that has a mean of 0 and a standard deviation of 1. We want to draw that right underneath here, under this left one. So let's see. There. Not great, but perfectly serviceable. Mu z equals 0, and we don't need an envelope for this. It's always going to be 0, right? We don't need to pretend we don't know it. We will always know this. Sigma z equals 1. And then if we pull down x bar and this other thing, then this area in the middle should be also alpha big. Maybe it's 95%, maybe it's 99%. I don't know. It should be symmetrical. It's just hideously drawn, but this area is definitely going to be alpha. Whatever it is, we'll find out when we open the envelope. And at the top end of this alpha, just like at the top end of this alpha, we have x bar. At the top end up here, we have what we called z1. Okay, so now what we need to do, that's the end of step 2, because alpha is knowable, 1's known, 0's known. We don't know z1, and we would need to do some stuff, but step 2 is done. Step 3 is use z to get p or p to get z. We do have an area. The area is alpha. We don't see it yet, but we could figure it out, right? All we would have to do is open the envelope. But in order to find z, we actually need, we're going to need to use, we're using Excel, right, in this class, so norm.s.inv, and then we need the area to the left. So we need more than just alpha. We also need this area here. Now, if you look back at the previous video with the numbers, we did calculate this, and I showed this formula, but I want to walk through the intuition again. If this middle is alpha, then these two tails combined are the complement of that, right? So together, these make up 1 minus alpha. Now we don't need both of them. We only need one of them. So if all we want is this right side right here, this area right here, this is half of that. This is 1 minus alpha over 2. That's that area. So the area to the left of Z1 is alpha plus 1 minus alpha over 2. Make sense? So what we are going to do is we're going to plug in norm.s.inv, and then in that we're going to put alpha plus 1 minus alpha divided by 2. And when we put that in, that is going to spit out a value that we are going to call z subscript alpha. I'm just going to give it that name, z subscript alpha, as a placeholder, okay? I don't know what the actual value is. It's going to vary in some sense, depending on what alpha is. But it is connected in this way that we are now naming this number, z alpha, as the z you get when you plug in this formula, right? So this is a definition. Z alpha equals this thing here. Okay, once that's done, that's the end of step 3. We may not have z, but we have the tool to get z as soon as we open the envelope, and I'm just trying to postpone that as much as possible. Okay, so once that's done, now we can do step 4. Step 4 is the z-score formula. The z-score formula in this scenario we said is going to be, that's the background, here we go. Z equals x bar minus mu x bar over sigma x bar. That's the general form. In this scenario, we actually have z alpha, plugging in values, equals x bar minus mu 1 over sigma x bar. And z alpha we could calculate. We have the calculation right here. X bar is going to be given. Sigma x bar is going to be something we already calculated or could calculate. And then mu 1 is our unknown. But since we have 3 of the 4, we can now solve for mu. To do that, we need to get mu by itself. So first things first, just like we did before, we're going to multiply both sides by sigma x bar. Flipping over the equal sign, we get x bar minus mu 1 equals z alpha times sigma x bar. And then we need to get rid of the x bar on both sides, on the left side. So let's see, subtract x bar, these cancel. We get negative mu 1 equals negative x bar plus z alpha times sigma x bar. And then we need to cancel out that negative sign. So if we multiply both sides by negative 1, we get mu 1 equals positive x bar minus z alpha times sigma x bar. Ta-da! Now we could open it up if we wanted to. And if we did want to, what you would see, if you looked at the numerical example I did in my previous video, it would look very familiar, right? What we would have is the 325 would go here. This would be 1.96. This would be 4.24. And sure enough, that was the answer that we got for the previous problem. But the nice thing about this formula is it doesn't matter what problem you're dealing with. This is now a formula that will generate lower bounds. This mu1 is called a lower bound. And this will generate lower bounds. It'll spit out lower bounds. You do have to go through the work. X bar is given. You have to use the formula to find z. You have to use the formula to find sigma. But it's a very straightforward way to get these mu1s now without ever having to draw all that stuff, right? This is a permanent solution to mu1. Okay, so we're halfway done. Let's solve mu2 side. We're going to go to the other side. Okay, so we finished the 4 steps for one side. We've already finished step 1 over here. Let's move along to step 2. Which is to relate this green one, the mu2 distribution over here, to the standard normal. So underneath this, I've got a z distribution right here. Mu2 corresponds to mu z. That's 0. Sigma z equals 1. If I trace this down, this will be my value z2. This right here is the other side of the middle, and then we know this area is alpha. and my z is at the bottom end of this alpha. All right, that is the end of step 2 for both of them now, not just the one. Step 3 is to use area to get z. If we want to get z2, we can, but actually what we'll find is that it's always going to be exactly, because it's symmetrical, it's always going to be exactly the opposite of z1. So we could plug it in like we did in the previous mathematical or numerical example. I'm actually just going to take advantage of symmetry and say it is the mathematical opposite of z, which means it's going to be negative z alpha, right? And if you want to test it out, you can, because it turns out if you just plug in norm.s.inv of 1 minus alpha over 2, it'll give that to you. But it'll always be exactly the opposite of the z alpha we got before. So rather than invent a whole new notation, z alpha 1, z alpha 2, I'm just going to put a minus sign here, and that will work for us. But that's the end of step 3, right? We use alpha, what we know about alphas, to get our z. And now we're on to step 4. Step 4 is to use this z-score formula to find our mu2. So we've got, again, plugging in, we've got negative z alpha equals x bar minus mu2 over sigma x bar. To solve for this, we can multiply both sides by sigma x bar. These cancel. And then flipping over the equal sign, we get x bar minus mu2 equals negative z subscript alpha times sigma subscript x bar. We've got x bar where we don't want it. So let's add x bar to both sides, or subtract x bar from both sides, sorry. I don't need parentheses, what am I doing? Go. These cancel. And we are going to get negative mu2 equals negative x bar minus z subscript alpha times sigma x bar. Last things last, we need to multiply both sides by negative 1. Cancel these out, right? We get mu2 equals positive x bar plus z alpha sigma x bar. And just like before, this would be 325, 1.96, 4.24. But again, what we have done is solve this problem for once and for all, where this is calculating our upper bound. Now, these are sufficiently similar that you can see that they're closely related, and often they are presented combined. mu1 comma mu2, that's the lower bound, that's the upper bound, equals x bar plus or minus z subscript alpha sigma x bar. Sometimes it's also written as just this one just expanded, or not compressed. Another way to write it would be x bar plus or minus z alpha sigma x over the square root of n, which just makes it a little bit more explicit what's going on here. I find it a little more confusing, but it's easier to know what plugs in where. The other thing about terminology, so this is the interval. The interval is the area between the lower bound, the region between the lower bound and the upper bound. So those are kind of the addresses that give us edges there. The other piece of terminology is that this thing right here, this is known as the margin of error. And usually when we do this, we would calculate the margin of error, or the MOE, first, and then we would take x bar minus it and x bar plus it. So another way to write this would be to write the margin of error equals z alpha sigma x bar, and then to write mu1 comma mu2 equals x bar plus or minus the margin of error, where it just breaks it into those two steps. So what does this look like in practice? Well, now when I go back to the problem that we did before, last time, you can see I still have these numbers up here. What I can do now, let's imagine that I just opened the envelope and I found these 4 values that were in the envelope. Now what I need is I need my z alpha, and I need my sigma x bar, and then I need my margin of error, and then I can find my lower bound mu1 and my upper bound, or mu2. So z alpha is going to be, we said it's the norm.s.inv. Let me find the formula of alpha plus 1 minus alpha divided by 2. So that's my norm.s.inv. My sigma x bar is sigma divided by the square root of n. My margin of error is the product of these two numbers, 8.32. And now my lower bound is my x. Here, I need to show you the formula. My lower bound is the x bar minus my margin of error. And my upper bound is my x bar plus margin of error. So you can see that now that we know this, we don't have to set up the problem every time the way that we have been setting it up with the two drawings and copying it down and doing all that stuff. The reason we had to do that was so that we could get to a place where we had a z-score formula we could solve. But the z-score formula is a very inefficient machine for generating mu's, because every time you want to get the mu, you have to do a bunch of algebra to get it out. What we did this time was we did all of the algebra first with just the symbols, so that we could figure out when you have your x bars and your z's and your alphas and your sigmas and your n's, what do you need to do to them to get a mu1? What do you need to do to them to get a mu2? And in so doing, we generated some mu-producing machines, one for the lower bound, one for the upper bound, and we combined them in a kind of, aesthetically appealing way, at least, concise way. And now, from now on, whenever you're doing a confidence interval problem, you don't have to go through any of this process. You can just take advantage of, if you know sigma, and you know x bar, and you know alpha, and you know n, if you know the stuff you need, you can just get right to the finish line. Run right to the question asks for a lower bound, calculate a lower bound. Question asks for an upper bound, calculate the upper bound. But what I do want you to know every time you do that, this right here is just a z-score formula, like the relationship embedded in a z-score formula converted into a mu generation process. This right here is just a different z-score formula, and this formula right here, which I'm sure you've seen before, mu1, mu2, x bar plus or minus z alpha. I know you've seen it before. Now you know it is two z-score formulas mushed together in a way that produces bounds. So you can use it responsibly now. Good luck. Have fun. Hopefully it makes your problem set 3 go quite a bit faster. And I'll see you guys next time. Next time we're going to look at what happens when we don't know the standard deviation of the mean. The standard deviation of x of the population. So how do we deal with that? We're going to learn a whole new distribution. We're going to learn some new Excel formulas that will help us. And the beautiful thing there is we will no longer have any terrible assumptions. So I'll see you guys next time. It'll be fun. Bye.